I do want to thank the organizers for inviting me and thank you all for coming. I want to talk this week about intersection theory. And of course, the first thing I'll do is describe what I mean by that. But I do want to say right at the beginning, the real focus of these talks is going to be not so much about developing the technical theory of intersections, but rather how this idea is used in practice in algebraic geometry. So that'll be the focus. And hopefully today, in fact in the first half hour, we can describe the basic facts about intersection theory, and then we'll get started trying to develop them and use them in the way algebraic geometers do. One thing I want to say is I want to encourage you, ask you, please, to ask any questions. We have 5 hours to talk. It's better if you have a question to some aspect, or something I'm not saying right, or some definition that's unclear. Let's straighten it out now rather than, realize on tomorrow or Wednesday that nothing is making any sense anymore. It's better to take a little extra time now and make sure that we're all on the same page. So with that said, the starting point for everything I want to do, as it was more or less historically, is the theorem of Bézout. And Bézout says that if you have two plane curves, so that's plane curves over, say, the complex numbers, and these are plane curves, degrees, let's say d. The statement is, I'm going to give you a very, very sort of basic form of Bézout. If C and D intersect transversely, I don't want to have to keep writing this, so the usual symbol that's applied is you say C intersects D with a line through the intersection symbol, meaning they intersect transversely. If they intersect transversely, then the actual number of points of intersection is D times E. And again, I expect that many of you have seen much more general forms of Bézout's theorem, but this is just the starting point, so let's focus on the simplest possible case. The main thing I want to say about this is that we should think about this as a theorem, not about the number d times e so much, as simply the fact that this cardinality of intersection does not depend on the particular choice of C or D, subject only to this hypothesis that they meet transversely. The point is, if I simply told you that the number of points of intersection of two plane curves was independent of the particular curves, then you could easily recover the number, in this case d times e. You would, for example, you could choose an example. You could take C to consist of d lines and d to consist of e general lines, and of course the number of points of intersection would just be d times e. So the real content of this statement is what was called in the 19th century the preservation of number. That the number of points of intersection is invariant under, so to speak, a continuous deformation of the two objects, the two curves. So, in that context, I should mention at this point the first of several dubious historical assertions. Robin knows much more about this than I do, so again, if I'm saying something wrong, you should feel free to correct me. But there was a fundamental shift in algebraic geometry at the beginning of the 19th century, which led to the development of the classical subject over the next century and a half. And basically, when people first started thinking about polynomials in two variables, they thought about it in the way that anybody naively would. They were talking about real polynomials, and they would look at the set of pairs, set of solutions, pairs of real numbers which satisfied the polynomial equation. In other words, they were looking at what we would now call real affine plane curves. There were two fundamental changes, as I say, that took place at the beginning of the 19th century, and they're both in some sense due to Poncelet. Poncelet was a French mathematician, I think, who was conscripted during the wars between France and Russia. He was captured and spent some years in a prison camp. And during this time of enforced isolation, he started thinking about this, and he had a problem. He said, you know, basically something is wrong, because when you ask, you know, when you try to solve a pair of, say, simultaneous linear equations, when you try to take the intersection of two lines in the plane, the answer depends on the lines. Two lines can either intersect and have a, or they can be parallel. Poncelet said we should avoid this. And so Poncelet proposed to work instead in projective space rather than in affine space. In other words, add points of intersection of parallel lines. Once you do that, then in fact every two distinct lines meet in a unique point. The second thing Poncelet said was, he's still not happy, right? He says, okay, now we've got lines straightened out, but what about, you know, higher degree curves, or even just lines and conics? If I have a line and a conic, I would expect, algebraically, I would expect two solutions, right? If I just substitute the equation of the conic in the line, I get a quadratic polynomial in one variable. That should have two roots, but it may not. It might be that the line is disjoint from the conic. Again, the discriminant of that quadratic polynomial could very well be negative. And Poncelet says, that's not good either. And let's fix that by working over the complex numbers rather than over the real numbers. They didn't have the notion of algebraically closed field in those days, but the complex numbers are right there, and that solves the problem. So those are two fundamental changes, going from affine space to projective space, and going from the real numbers to the complex numbers, that really fundamentally altered the subject. And they formed basically the ground of the foundation of almost all of 19th century algebraic geometry. They were, I guess I gotta say this parenthetically, that they were not well received at the time, initially. I mean, because you were trading something that was very concrete and geometric. You know, a real plane curve in R2, you were exchanging it for something very difficult to visualize, very abstract seeming. Now we're talking about projective space rather than affine space, and you're talking about projective space over the complex numbers. And it's not easy to visualize anymore what you mean by the solution set of a polynomial. Everybody can draw a conic on the board, or at least I can sort of approximate one, but to write down an actual set of complex solutions of the corresponding polynomial in projective space is much harder. And in fact, it's interesting to me that many of the sort of people who resisted this commented in a way that was echoed a century and a half later when Grothendieck proposed that we work with schemes rather than varieties. People said, well, yes, you know, by introducing these changes, you've arrived at a theory with a lot of formal and abstract symmetry, but at the expense of intuition, visualization. And now, 2 centuries later, of course, nobody, I think, would ever conceive of going back. So now we're in projective space over the complex numbers. And this is Bezout's. Okay. So what do we want to do now is, what I'm going to propose is to take this idea of Poncelet's, which is expressed in the Bezout here, the idea of preservation of number, or invariance of intersection under deformation. And I want to see whether it can be applied much more broadly. By much more broadly, I mean take, instead of P2, we're going to replace P2 by pretty much an arbitrary, smooth, projective variety. X, and X will have dimension n just to give it a name. Okay? And the question is, if we take, so to speak, the analog of two curves in the plane, if we take, say, y and z, subvarieties in X of complementary dimension. Complementary dimension. Can we say that the analogous statement is true? Namely, don't, again, forget the number, but just ask, whether the number of points of intersection, assuming y and z intersect transversely, is in fact invariant under, so to speak, continuous deformation. And the answer again is yes, in this kind of generality. So there's really a fundamental principle here that we're going to try to develop over the next few minutes. Okay. So again, let me just write this down. If y intersects z transversely, the cardinality of the intersection is invariant under deformation. In a suitable sense of y and z. Well, we still have a little bit of a ways to go. For one thing, what I'd like to do is to get rid of this complementary dimension. In P2, we don't have a lot of room to work, but in general, if we have a higher dimensional variety, we want to intersect subvarieties. We could intersect, a priori, we can intersect subvarieties of any dimension, any codimension, and ask if we can describe, in some sense, the intersection cycle, the intersection of the two varieties. But in any case, what we need in order to do this is to make a little bit more precise the notion of what we mean by a family of varieties, and, or equivalently, what we mean by under deformation. What does it mean to have a family of subvarieties? And the answer is, let me just say this. We say that two subvarieties, say y and y prime, are rationally equivalent this is the term. If, well, I'll just say this, so to speak, colloquially first, and I'll try to give a slightly but not completely more precise definition. If there exists a family of subvarieties parametrized we're trying to work entirely algebraically, so I don't want to talk about continuous deformation. I want to say that two things are equivalent if we have a family of subvarieties parametrized by an open subset of an algebraic, connected algebraic curve, like P1, and including both y and y prime. Now, again, what we mean by a family, this is the sort of standard definition of algebraic geometry. What we mean is a subvariety z sitting inside P1 cross x, such that if I intersect z with the fiber of this over 0, say 0 cross x, I get back y, and if I intersect with, for example, the fiber over infinity, I get y. So this is, so to speak, our notion of a continuous deformation. We are just looking at families over P1 and saying that any two fibers are declared to be equivalent in this sense. Now, just parenthetically, this seems like an extremely restrictive notion of equivalence. I mean, we want to talk about curves, or sorry, subvarieties belonging to a family. Why do we insist that the family be parameterized by P1, for example? And the answer is, there's no good reason. This is an extremely, and I'll talk more about this in a moment, this is an extremely fine equivalence relation, meaning it's very difficult to get things to be equivalent. If you have a rational variety, so there's lots of P1s, or if you have a homogeneous variety, where you have a group acting, it's very easy to generate equivalences. But in general, it's very hard. If I give you, for example, something like a quartic surface in P3, that's the first degree of a surface that's not rational, and I give you 2 points explicitly, there is no way you can tell me if those 2 points are rationally equivalent. Unless you get lucky, and there happens to be a visible rational curve containing both of them, and then you can move one point to the other along that rational curve. But in general, this is not a nice equivalence relation. And again, I'll talk more about that a little bit later on. The reason we do it, by the way, is because we're going to prove a sort of analog, again, of Bezout's theorem that says that the intersection of equivalent subvarieties is equivalent. And the finer the equivalence relation, the more information that gives us. So we choose this very restrictive equivalence relation simply because we can. It gives us extra information. The unfortunate aspect is we have no way to use that extra information, but it's free, so why not? It's like going to a store and they offer you, if you buy item A, you get item B for free, and you know you're never going to use item B, but it's free, so you take it anyway. And if you'd rather think of a more reasonable equivalence relation, you should feel free to do so. You won't lose anything, at least as far as what we're going to be doing this week. Okay, so now, having defined that, let me make one more definition. Again, we define an equivalence relation. And we have a corresponding notion of cycles or subvarieties mod equivalence relations. So let me make a couple more definitions. So first of all, a cycle of dimension k on X. Well, this is a very 20th century trick now. We're just going to, almost automatically in these situations, we look not at subvarieties, but formal linear combinations of subvarieties. It's a formal, finite, integral linear combination of subvarieties of X of dimension k. So typically something is written A is the sum ni ai, where the ni's are integers, and can be positive or negative. So we want to, that's the main reason for doing this. We want to include linear combinations that have negative coefficients as well as positive, and that's going to be necessary for the basic tool we're going to be using. Then we define the kth group of Chow k cycles, ak of X, to be the space of cycles of dimension k on X. So again, just subvarieties of dimension k modulo the equivalence relation generated here by rational equivalence. In other words, we have a subgroup of these consisting of the difference of rationally equivalent cycles. We take the subgroup generated by those differences and we mod out this, take the group of all cycles modulo the subgroup generated by those equivalences. Now I'm sweeping, Robin looks troubled here and I can see why.
Suppose you have an irreducible variety.
Exactly. I'm sweeping under the rug a fair amount of dirt. In fact, forming a distinct bulge, which is causing Robin some distress, and as I say, justifiably. The problem is here, we're looking at subvarieties of P1 cross X, and implicitly I'm assuming that the fibers I'm looking at are irreducible again. What if the fiber here actually happened to be a reducible curve? Well, we'd like to say we just add up the components of that fiber. And then we get into a further issue, which is we have to ascribe some multiplicity to those. In other words, it could be, for example, that if I could have, just in P1, I could have a family of cycles that looks like this. So I have 2 points in the general fiber, specializing to 1 point in the special fiber. And again, I don't want to say that 2 points are rationally equivalent to 1 point. I want to assign a certain multiplicity, and I want to think of the fiber here as not the point, but the cycle 2 times the point. But let me just leave it at that and say that underlying all this, you have to have a notion of what it means for a component of a fiber of a one-parameter family to appear with multiplicity. And then you can extend this notion of rational equivalence to cycles, and then you can mod out by this rational equivalence. So, thank you. Yeah. Excuse me, can you repeat?
The of negative plus with coefficient reactives.
Sorry, coefficients in what?
Less of 0. Less than 0.
Oh yes, negative coefficients. Right?
Yes.
So why are we allowing this?
Why
That will come up in a moment. Why do we want to include these?
Una equivalence.
Yeah. Well, basically, what I want to say is rationally, in this situation, for example, if I do have a family Z, right, with fibers y and y prime, I want to say that the cycle y minus y prime is declared equivalent to 0. So if I want to think of this as a cycle and take the subgroup of cycles generated by things in this form, I have to include negative coefficients. I want to take differences of cycles, not just sums. Okay. So now, having said that, let me introduce one more bit of, this is just purely notation, and then we'll state the sort of first of two basic generalizations of Bézout. So, one more bit of notation. Here I've indexed cycles by their dimension. It's also common to write AK of x. And this is really just the same object, but just indexed differently. These are, again, is the cycles of codimension, K in x. So that's codimension, again, mod rational equivalence. All right? And so all I've done is move the subscript and superscript and change the indexing. If Bill Fulton were here, he would be making a face even worse than Robin's. And I'll talk more about that too in the future, but basically he likes to reserve this symbol for special circumstances. Fortunately, that special circumstance applies if we assume that x is a smooth projective variety. But, so I warn you right now that while we can define the object on the right for arbitrary x, not necessarily smooth and projective, you're not supposed to use this symbol in Bill Fulton's presence. Okay? And there's good reasons for that, actually, which will become clear in just a moment. Okay, so now the theorem is this. And this, again, I want us to think of as a vast generalization of Bézout. Again, assuming x is simply smooth and projective, but not assuming anything else, that there exists a bilinear map from AK of x cross AL of x for any integers, natural numbers k and l, mapping to AK plus L of x, such that, so this is now on cycles, mod rational equivalence, and the key condition is that if y and z in x intersect generically, and these can be arbitrary dimensions, so I don't want to require that they intersect transversely, I just want to require that they intersect generically transversely. And what that means is, of course, the intersection may have several irreducible components. At a general point of each irreducible component, the intersection is transverse. If I were to define multiplicities, I could also say that the multiplicity of each component of the intersection is 1. So at a general point of each component of the intersection, a general point of each component of the intersection is a smooth point of y and z, and the tangent spaces together span the tangent space to x, transversely. I don't have a symbol for intersect generically transversely. If anybody has a suggestion, I am open to suggestions, except to write a G or something underneath the standard transverse symbol. Okay? So we'll do that. Hopefully it won't come up too much, because that's an ugly looking symbol. So this is the end of the statement, and this is what I would call sort of Bézout's theorem for x.
You haven't said the statement.
Yeah, no, I have. There exists a bilinear map. Such that, oh, I'm sorry, you're right. I just thought it was a little short there. So if I have two subvarieties, what I want to say is that the class, now here, I'm going to introduce one bit of notation here. If y is a subvariety, if then by square brackets y, I'm going to mean the class of y in A of x. Okay, so that's just the cycle y, or the subvariety y, modulo the rational equivalence. The claim is that the product of the classes of y and z is just the class of the intersection. Now I've got a statement. Grammatically correct. This is, again, the strength here says, right, that if I chose rationally equivalent cycles, if I chose say y prime, which was rationally equivalent to y, and still met z generically transversely, then the class of the intersection would be the same as it was before. The class of the intersection depends only on the classes of the cycles that you're intersecting, assuming generic transversality. So that's the content of this statement, and this is the first of the two sort of main theorems of intersection theory, just the existence of this product. Having said that, I can now, of course, combine all these maps. These intersection maps, intersection products, give the ring A of x, which we define to be just the direct sum of these groups, AK of x, the structure of a commutative graded ring. Okay? So let me stop for just a second here and ask if there are questions. How do you prove something like this? It's actually not so bad, and I should say a word about this too. Classically, what was done here is to prove this based on what was called a moving lemma. And while I'm not going to prove this, it is written down in a lot of places, and I would like to at least indicate what the basic mechanism is. It's a very elementary statement, and it's something that is both plausible and geometrically meaningful. It says, the basic idea is we want to define an intersection like this, and the problem a priori is that if I have simply two classes of cycles in X, so a class in AK and a class in AL, in order to define the intersection class, I want to find a pair of cycles representing those classes that do in fact meet generically transversely. And it's not obvious I can. And that's the content of the moving lemma. So the moving lemma says two things. One is, if A and B are cycles on X, then there exists another cycle A prime rationally equivalent to A. This is going to be the symbol for rational equivalence, such that A prime intersects B generically transversely. So if I have two cycles, if I just choose arbitrary cycles representing two classes in X, call them alpha and beta, then even if they don't intersect generically transversely, I can replace one of those cycles by another cycle representing the same class that does meet B transversely, generically transversely. And, of course, the second part, and the key really is that the class of the intersection is independent of the choice of that other cycle. So that tells me that, in fact, if I intersect two cycles, assuming generic transversality, the class of the intersection depends only on the class of the two cycles that I'm intersecting. And again, this is the ultimate sort of form of Bézout. Okay? And let me, in fact, since I've said now several times that this is a generalization of Bézout, let me just write Bézout in these terms. Bézout says that if I look at the ring associated to projector space, this is called the Chow ring, what I get is that in every degree, from 0 up to n, it is just Z. Two subvarieties of projector space are rationally equivalent, of the same dimension, are rationally equivalent, if and only if they have the same degree. And the statement here is correspondingly that the Chow ring is simply generated by the class of a hyperplane modulo the one relation that the hyperplane to the n plus first power, well, that is now necessarily 0, and we're going to mod out by that. So zeta is the class of a hyperplane sitting inside P. And again, this is sort of clear. Once you have this statement, you just say, well, look, two hyperplanes intersect, if they intersect transversely, if they're distinct, they intersect in a codimension 2 plane. In general, a n minus k plane and an n minus l plane, if they intersect generically transversely, will intersect in an n minus k minus l plane. And so you have this structure. I keep saying this is the first part of the basic theorem of moving, of the intersection theory. We have one more to go, and then we're going to be free. We'll have a little comment period, and then we'll be free to actually start applying these ideas, seeing what they tell us in practice about the behavior of varieties. So let me, in order to do this, let me move back over here and start on a clean board. Well, again, I think the whole subject is, in some sense, a strange mix of 19th century mathematics and 20th century mathematics. And if I could just think about this through a 20th century lens for a moment, you know, having defined, having associated to every smooth projective variety in this way, a graded ring, the first question anybody would ask in the 20th century is, well, is this a functor? In other words, how does this assignment of a ring to every projective variety behave under morphisms between such smooth projective varieties? So let me just take a moment now and say what the answer to that is. And again, this is going to be a theorem. It's going to be based on a version of the moving lemma, which again I'll state, but I'm not going to prove. So the basic idea, and this is the simplest thing in the world. If I have a map, so let's say x and y are smooth projective varieties. Now, of course, they may not have the same dimensions. I'm going to call the dimension of n, of x, n, and I should give a name to the dimension of y. I'll call that m. And I want to say f from x to y is just any morphism. What is the relationship between the Chow groups? Or what relationship does this morphism induce between the Chow groups? And the answer is the simplest thing. Just the key to thinking about all these problems is just to think of these in terms of the most basic set theory. If I have a subset of x, what can I do with it? I can take its image. If I have a subset of y, what can I do? I can take the pre-image. And those are the two basic operations. Again, as always, subject to some conditions about a sort of transversality. So let me say that. So then we have, this is again, we're getting into the realm of theorem, there exists a push-forward map from A of x to A of y, which simply sends the class of a cycle, I'm going to have to call cycle z now since the letter y is taken, f lower star of z is, well, here's the thing. I want to See, if I have a map here, right, the image may have lower dimension than the original variety. And in that case, I just want to set the push forward of the class equal to 0. If the dimension of f of z is strictly less than the dimension of z. So I only want to take push forwards when the cycle maps to a cycle of the same dimension. And in that case, I just want to take the push forward of the class of z to be the class of the image. But I can't. Because, of course, I have the same situation as before, that if I have a, for example, let's see how to say this. If z, now let's assume that the image of z has the same dimension as z, then the map from z to its image will be generically finite. It'll have some degree. And I want to take that degree as a sort of multiplicity. In other words, here again, let's take that simple example of mapping, say, P1 to P1 by the map z goes to z squared. If I have 2 points on the domain, they'll, of course, just map to 2 points on the target. That's not a problem. But if I have 2 points that are aligned, I don't want to say that the image of the sum of those 2 points is just the image point. Again, I want to say it's the image point with multiplicity 2. So what I want to do is to take the class of the image, f of z, but I want to multiply by m, where m is the degree of the map f from z to f of z. So again, if the image has strictly smaller dimension, I just set the push forward of the class equal to 0. If it has the same dimension, I take the image, but multiplied by the degree of the map. This is a sort of elementary process. I don't need a lot. I mean, I have to check a lot of things. But I don't need, for example, a moving lemma to establish this, because in effect, I've told you what the push forward of the class of z is without any requirement, any restriction on z.
You use m twice.
Where?
Is it the same name?
Which?
Oh, dimension of
Yeah, with m.
Not the
Dimension of y.
Dimension of y.
Oh!
Sorry.
D.
Ah.
Big D.
So what's your D, I guess?
D is nice.
Yeah, D is nice. For a degree, why not? Okay, so thank you.
And want z to be reducible?
I want what?
Z to be reducible?
Yes. Yes. I mean, always with these definitions, we're going to define the object in question for the class of an irreducible subvariety and then extend it by linearity to arbitrary cycles. Now, again, that's the sort of relatively elementary part of this. And there's 2 parts, 2 assertions. Actually 3, but we'll come to the third in a moment. I also want to say that there's a map in the other direction, which is simply the pullback map. And that map goes, again, from A of y to A of x. And here, in some sense, it's even simpler. I want to say that f upper star of the class of a subvariety, I guess I've got to use another letter, because this is now going to be a subvariety of the target space y, is just the class of the pre-image. But here I have to make an assumption about how this is positioned, assuming that the pre-image, f inverse of w, is generically reduced. In other words, again, has no multiplicity of the same codimension as W. So again, all I'm doing is taking pre-images, but in this case, I have to be cautious. You know, the standard example of something where this doesn't, so to speak, work is if you take something like a blow-up map. You take the plane or any surface and you blow it up. So you have an exceptional divisor. The exceptional divisor lives over a point. If I want to take the pre-image of a point, again, I want to get something of codimension 2. If the point I'm taking the pre-image of happens to be the point I blew up, the pre-image is codimension 1. I don't want to count. I don't want to allow that. Okay? And that, unfortunately, means that we have something to prove here. Because we need to say that given a class in A of y, given a class in the Chow group of y, I can find a representative cycle that satisfies these conditions. And I want to say that the class of the pre-image doesn't depend on the choice of representative in y satisfying these conditions. It depends only on the class. And that way, I get a well-defined map backwards. Pull back. So again, this statement, this part here, we need a variant of the moving lemma. And I think rather than write it out, I'll just say it again. We need to know that given a class, why don't we just write it? Given a class alpha in A of y, there exists a representative cycle A, let me in fact specify the codimension here, A of codimension K, such that, I should maybe call the cycle W. So the class of W should be the class alpha, and W satisfies this condition. The pre-image is generically reduced of the right dimension. Okay. So we're just about done. We have one more statement to make, and fortunately, it's sort of the most obvious thing in the world. Again, if I just think in terms of sets, if I have a map between two sets, x and y, and I have maps correspondingly between subsets, I associate it to a subset of x, I can take its image in y, associate it to a subset in y, I can take the pre-image in x. The basic relation between these two operations is what's called the push-pull formula. This is very colloquial, and I'm not sure it's standard, but it's easy to remember in any case. The basic statement is that if I start with a class alpha on x and a class beta on y, I can do two things. I can push alpha forward and then take the product with beta, intersect with beta. Or I could take the pre-image of beta and intersect that with alpha. Sorry, I said that backwards. I could take alpha, that's the cycle in the domain, and intersect it with the pre-image of beta, the pullback of beta. And the relationship between these cycles is that one is simply the image of the other. So one of the virtues of using the moving lemma to establish these facts is that you get formulas like this for free. All I have to do is say that I can find representative cycles for these classes alpha and beta that are suitably transverse. And then this becomes, simply this reduces to a set theoretic statement. So again, the whole idea of the moving lemma is to convert statements about these Chow groups and cycles, mod rational equivalents, and their behavior, for example, under maps, convert them into sort of statements at the level of sets. Are there any questions? Yeah.
Like this, F upper star is probably a ring homomorphism?
Yes.
Lower star.
Yeah, exactly. One way to say it, I didn't say that, and in fact, thank you, I should have. F upper star is a ring homomorphism. It's a homomorphism, in fact, of graded rings. It preserves grade. F lower star is not. For one thing, it messes up the dimension. It keeps the dimension, but it messes up the codimension correspondingly. If the dimension of y is not equal to the dimension of x, since I gave these guys dimensions names, I should use them, right? Here, I want to say if I start with a cycle of codimension k in x, I'm going to wind up with a cycle of codimension n minus n plus k in y. On the other, the pullback map, of course, preserves codimension, And as I said, this is a ring homomorphism. This, one way to interpret the push-pull formula is to say that this is a map of, sorry, the superscript in the wrong place. Is to say that the push-forward map is a module homomorphism. As I can think of the Chow groups, or the Chow group as a module. Oh, pardon? It's a module homomorphism. So, in other words, if I think of the Chow ring itself as simply a module over itself, this is saying that the push-forward map is a module homomorphism. It's a homomorphism of modules, where you have to mix them up. So I have a number of remarks to make. We're almost done here for the day. Yeah.
Minus plus A.
Pardon me?
M minus N plus A.
Oh, yes, yes, yes. Sorry. Did I get that right the first time and then miscopy it? I hope so. Okay. Thank you very much, yes. So in other words, the degree, so to speak, is shifted by the difference in dimension. So let me take a moment out, and I'm going to deliver now a second historically dubious assertion, which again, Robin can correct me. But the one thing I feel needs to be said here is that this was, in some sense, the original construction of a notion of cycles module equivalence relation. This predates, for example, homology and cohomology. In fact, if you look at what's on the board, it looks an awful lot, formally, like homology and cohomology. We have homology, which is indexed by the dimension. We have cohomology, indexed by codimension. We have a ring structure on the cycles, in which case, analogous to cohomology, the cycles are indexed by codimension. We have push-forward maps and pullback maps. We have, and of course, in this case, intersection products are the same thing as cup products or cap products. Either way, because we've implicitly identified what we would call homology and cohomology. In fact, it's worth pointing out that this was the original model for the notion of homology and cohomology. Poincaré, this existed at the time of Poincaré. Poincaré knew this whole theory, was what's on the board in some form or another. He knew it very well. And he wanted to know, could we do something like this, analogous to this, for submanifolds of a compact-oriented manifold? And at first glance, it seems that you can. In fact, it's at more than first glance. So Poincaré's whole idea was do this for oriented submanifolds. Now we're working in the C infinity category, differentiable manifolds, oriented submanifolds of a compact oriented manifold. And the question is, does it make sense to talk about the intersection of two submanifolds as invariant under continuous deformation? And it looks like it does. In the standard, the simplest example is to take a torus. Okay? And look at cycles. Let me see if I can actually use this colored chalk. Look at cycles like this and like this. Well, maybe not. So this we'll call alpha, and we'll call this one beta. And visibly, they intersect in one point. And what's more, if I deform either of these submanifolds a little bit, they still intersect in one point. I cannot make them disjoint under continuous deformation. And likewise, if I took two cycles that are homologous, though of course he didn't have that term at the time, to beta, they seemingly don't. Now there's a problem here, which is to say, I could in fact deform alpha in such a way that it, of course I can't make it not meet beta, but it might meet beta more than once. I could have a cycle that looks like this, well, beta as it was before, and then alpha could look something like this. It could come through, cross, and cross again. Now it seems that you have 3 points of intersection rather than 1. So Poincaré figured out what to do about that. What he says is you have to assign, assuming that these two submanifolds intersect transversely, you have to assign a sign, plus or minus 1, an index, to each point of intersection, reflecting the relationship between the orientation of the two cycles and the orientation of the ambient manifold. Remember, we're assuming that the ambient manifold is itself oriented. So if we think of these as oriented submanifolds, then at every point we have a tangent vector, and for each of these two subvarieties, and if I want to intersect one with the other, at each point of intersection, I take the index to be the relationship between the orientation of the ambient manifold and the orientation I get by taking the orientations of the two submanifolds in turn. And once you do that, you see that of these 3 points of intersection, 2 appear with a plus sign, 1 with a minus sign. And so you're back to being in business. You have a well-defined total number of points of intersection. And that was Poincaré's observation. It's a well-defined sort of bilinear intersection product on submanifolds of a given compact-oriented submanifolds of a compact-oriented manifold. Now, if you want to know, if you've ever been curious how Poincaré proved Poincaré duality, which is an assertion about an isomorphism between homology and equality between homology and cohomology, 30 years before cohomology was invented, this is the answer. What Poincaré proved, in effect, was that this intersection product on homology defines a non-degenerate pairing between homology groups of complementary dimension. That was the original statement of Poincaré duality. So now something amazing occurred in the next few decades after Poincaré. This is limited very much to being on manifolds. There's no analogous statement of for homology groups on a singular space. Well, I mean, there is in a sense that McPherson developed this whole notion of intersection homology, which we can talk more about at some point, but not now. The point is, what Poincaré said was just a theorem about homology, about intersection products on homology. But then, when cohomology was introduced, was that in the 20s or 30s? Something around then, right? When cohomology was introduced, Poincaré duality was reinterpreted as asserting an isomorphism for a compact smooth manifold between homology and cohomology. And in those terms, it was observed that if you ported over the intersection product from homology to cohomology via this isomorphism, you got a ring structure on cohomology. And then the most amazing thing of all, and I still don't know how to account for this, is if you look at that ring structure on the cohomology groups of a compact smooth manifold, which was gotten by applying Poincaré duality to the intersection product on homology, that ring structure existed for an arbitrary, more or less arbitrary, singular space as well. So even though we were led to this description of the product by looking at intersections and homology on compact-oriented manifolds, once we passed over to cohomology, the product structure, in fact, is defined much, much more broadly. This is a sort of unexpected bonus, and I'm not, as I say, sure how to account for this. All right. I think, let me see if there's something that urgently needs to be said. Let me make a couple quick remarks, and then we'll call it quits for today, okay? And then we'll get started bright and early tomorrow, and we'll actually start using some of this theory, calculating with these groups in practice and seeing what they tell us, what theorems in algebraic geometry we can derive just from knowing about the existence of these intersection products. The one, actually sort of two remarks I want to make. I said a good bit earlier this hour, this past hour, that child groups are in general fairly hard to calculate. And I want to stand by that statement. Okay, so I want to just make this comment. In general, child groups AK of X are impossible to determine. Now, you know, how it sort of contradicts what I said at the moment ago. I mean, projective spaces. And in fact, we're going to be spending the rest of the week calculating exactly these things. What do I mean by impossible to determine? Well, that's in general. And what I want to say here, and I want to make this very clear, is that we can describe child rings very explicitly and work with them very effectively in a very narrow range of varieties. Mostly homogeneous varieties or rational varieties or things that are not far removed from one of those two classes. Those are very restrictive classes of varieties. And in general, AK of X, we don't know. So for example, even if X is a surface, we don't know the group of zero-dimensional cycles. So that's just points. As I said before, if I give you explicitly a quartic surface in P3, smooth quartic surface, I give you the equation, I give you a point on the surface, I give you 2 points, there is no way of determining, in general, whether those 2 points are rational. In fact, Mumford proved a theorem that says that this thing is larger than we can possibly know. What Mumford proved was he said the following. Suppose I fix a base point in X, and I look at the map from the nth power of X with itself to, this is now going to be strange because I'm mapping a variety to a group, A naught of X. But it's simple enough. I'm just going to take the collection of points, P1 up to Pn, and I'm going to map it to the sum of the Pi's minus n times P naught. So I'm going to get a cycle of degree 0 in effect. What Mumford proved, now bear in mind, if this is a surface, this is a 2n-dimensional variety. Okay? And what Mumford proved is that if P of that surface is non-zero, it has a non-zero holomorphic 2 form, the fibers of this map, un, have dimension, all of them at most n. What that means, so we have a 2n-dimensional object here. We're mapping to the child group of zero-dimensional cycles. The fibers have dimension at most n. That means that this thing is bigger than we can possibly imagine. If this had any kind of structure at all of a variety, even locally, it would have dimension bigger than n for every n. So it's not just not finally generated as a group, it's not even, it can't even be generated by the points of a variety of arbitrary finite dimension. It's just, it's way too big. Okay, defined degree map from A naught of X to Z. In other words, rational equivalence preserves the sum of the coefficients. If you write a zero cycle as a linear combination of points, rational equivalence preserves the sum of the coefficients, and so we can talk about the number of points of intersection, even though we don't know the actual group A naught of X. So for the most part, this is what we're going to be focused on. All right, I started to run over time. I'll stop here and we'll continue tomorrow. Thanks.